Here's our last section, 12.9, determinants and vectors in three space, in three dimensions. And the cross product becomes a very key tool for what we're going to do in three dimensions. Because it actually produces a vector perpendicular to the plane of the given two vectors in the cross product. We had to wait to this point, though, because the cross product relies on evaluating a determinant, a very tricky kind of determinant that involves both scalars and vectors inside it. Now, first you have to learn this little I, J, K notation. I, J, and K. These are the direction vectors, the unit vectors, in each of the three directions. And isn't it nice and consistent there that we put I along the x-axis, J along the y-axis, and K along the z-axis?
Why not just call them x and y?
No. No, because we want to reserve that for the names of the coordinates, the points in three space. This is specifically referring to a vector that's only one long in the unit, in the direction of the x-axis, the positive x-axis. And as you're going to see in physics as you take next year, this is going to be very important when you study some electromagnetic forces and so forth. And the direction of the current flow will determine the direction of the magnetic field, all by a cross product to determine the way the right hand or left hand moves.
So when you gave us a problem, could you say like 3J and then be
3J would just be 0, 3, 0. Yeah. So there they are in the 3D space, right? The three unit vectors, I, J, and K. So let's write 3, 5, 6 in terms of unit vectors and graph it. So 3, 5, 6 is 3, 0, 0 plus 0, 5, 0 plus 0, 0, 6. Let's just split it up into 3. Okay? So I have both a sort of horizontal, vertical, and I guess, well, you can't really call it horizontal, vertical components in three dimensions. So the forward, to the right, and the up component, okay? And so this is thrice 1, 0, 0, and 5 times 0, 1, 0, and 6 times 0, 0, 1. And so that's where you get 3 I's, and 5 J's, and 6 K's. And so we can do that. We can go 3 I's, 3 of these in the I direction, followed by 5 in the Y direction, or the I direction, or J, 1, 2, 3, 4, 5, and then finally followed by 6 in the vertical direction. 1, 2, 3, 4, 5, 6. There you go. And there's your 3, 5, 6. That's that first technique we talked about, how you could locate a point by sort of going along in the X direction, Y direction, Z direction. You could also put it in your box again if you want to do that. But this is showing the vector 3, 5, 6 as a sum of scalar multiples of all the unit vectors. They're called unit vectors because they're one long, the unit that you're using on your axes. Okay, so now here's the cross product. To do the cross product of U cross V, you actually set up these unit vectors, I, J, and K, in a 3 by 3 determinant, along with the coordinates of the other vectors, the vectors you're trying to cross. So U cross V, we actually put A, B, C, and D, E, F in here, in the second and third row. And you always put in the top row the unit vectors, I, J, and K. Now this is actually going to give you another vector, because notice I just have the determinant symbol here. Not the absolute value as well, like in some of those applications. You had the further, you did the determinant, and then you did the absolute value to come up like the volume of that parallel pipette, or the area, and you had the two vectors in two space. Now, because we're not doing the absolute value, we're going to, when we do this determinant, we're still going to have vectors left inside. And it makes sense to do it by expanding by minors of the top row. Anything else gets kind of strange. I mean, eventually it would work out, but you don't want to do it that way, okay? We want to expand by minors of the top row, okay? So in this case, to cross 2, 3, 4, and 1, 0, 5, I'm going to repeat my unit vectors here, I, J, and K. I like putting those arrow symbols on top, just so I remember that these are not just numbers, they're vectors. And then the first vector is 2, 3, 4. Order makes a big difference on this. It wasn't such a big issue with dot product. That's because multiplication and addition were commutative. But now, as we can see with determinants, you do a lot of subtraction. We said before, if you switch the rows in a determinant, you change the sign. So the same thing here. To get your cross product going in the right direction, you've got to make sure you put the first vector here in the middle row, and the second vector, 1, 0, 5, in that row. Now, what's the minor of I, the vector I? 3, 4, 0, 5, right? 3, 4, 0, 5. It's what you get when you take out the row and the column going through I. Right? And then the minor of J, 2, 4, 1, 5. And the minor of K, 2, 3, 1, 0. So notice how we're always getting numbers again for these minors. Joy?
Minus J instead of thinking of I.
Exactly, Joy. Where were the rest of you on this one? Come on. You can't just follow me blindly, people. You're going to be running into walls all the time. So thank you, Joe. We need a negative on here because that vector is in a negative position when you expand out the minor. No. Remember, the negative coefficient only goes on the element of the row or column you're expanding. You don't change the minors at all. The minor is going to stay as the row and column going through J. When you take that out, you get 2, 4, 1, 5.
So you don't have to add the negative signs there?
Well, we're going to multiply the answer we would have had by a negative 1. Yeah. So, now you go ahead and figure out each of these. You get 15 minus 0 times I plus 10 minus 4, and it's going to be negatized, times J, plus 0 minus 3 times K. So that's 15 I's minus 6 J's minus 3 K's. And normally I don't leave it like that. We just kept the I, J, and K there as a way of separating out our components. It's a lot easier just to write it as 15, negative 6, negative 3.
And that's the cross product.
That is the cross product. Okay? Let's check it. If it's the cross product, it should have created something perpendicular to both the original vectors. So before we get into the properties, I just want to do this check here. Is 15, negative 6, negative 3 perpendicular to both 2, 3, 4, and 1, 0, 5? Okay, this half the room, test against 2, 3, 4. Go. Okay. This half the room, test against 1, 0, 5. Go. I will try to do both. And what is your test for this? The dot product. The dot product. Yes. From that negative that Joy brought up. The determinant is 10, but you have to multiply J by a negative 1 because it's in that negative position.
It works out. And then it equals 0.
Okay. 15, negative 6, negative 3, dot. 2, 3, 4. Then we get 30, and negative 18, and negative 12, 0, check. 15, negative 6, negative 3, dot, 1, 0, 5. 15, 0, negative 15, equals 0, check. It is perpendicular to both. Okay? Now, couldn't we have just maybe, some of your homework early required that you produce a vector perpendicular to another one. So you'd have a lot of choices, right? Usually you pick a couple values for A and B and see if you were the third one had to be make it perpendicular. But in this case, it's definitely a much easier process than trying to use trial and error and guessing vectors that would actually be perpendicular to both. I suppose you could set up an XYZ equation. You know, if we didn't know this 15, negative 6, negative 3, you could have said, well, ABC dot this equals 0 and ABC dot this equals 0. That would create two equations in 3 unknowns. Then you could arbitrarily pick one of the constants, one of the ABCs as a value and figure out what A and C is. Because, you know, this is not the only vector, 15, negative 6, negative 3, perpendicular to the first two. Any scalar multiple of this So 30, negative 12, negative 6 would also be perpendicular to the first two. So there's an infinite number of solutions that will be perpendicular to two vectors. Thing is, the cross product, though, the magnitude of the cross product also has varying in many application problems. So that's why you are just going to come up with one vector as a cross product. Because the magnitude of the original two vectors have impact on that. And that's what this page is all about. Properties of the cross product. We just demonstrated this first one, that u cross v is perpendicular to either of the original two vectors. Okay? That is not the only property. If you reverse the directions of v cross u with u cross v, you can see it's not commutative. What else would do this where you get the opposite answer when you reverse the operation? You've known this for a long time. Multiplication and addition are commutative. Subtraction is not. If you reverse the order of subtraction, you get exactly the opposite answer. And so too with the cross product. If you reverse the order of the cross product, you get exactly the opposite answer. It'll have the same magnitude, just exactly the opposite direction. Also now here, remember our dot product? You could also do it by the product of the magnitudes of the cosine of the angle between. Now you can get the magnitude of the cross product as the magnitude of the two vectors times the sine of the angle between. Also geometrically, the magnitude of u cross v is the area of the parallelogram formed by u cross v. So this actually finishes our thinking. Remember how we said, if you did a 2 by 2 determinant of two-dimensional vectors, it gave you the area of the parallelogram. And then if you went to three vectors in three space, it gave you the volume of the parallel pipette if you did the determinant, absolute value of the determinant. So how do you do it if you've only got, if you got two vectors in three space and you want to just do the parallelogram? Well, here's your answer. You can get the area of that parallelogram in three space by doing the magnitude of the cross product. Okay? Yes, this is the right-hand rule. Let's see how this works now. You got your right hand out, people?
Yeah.
This is how cross product works. First finger is the first vector. Second finger is the second vector. And your thumb then points in the direction of the cross product. Let's check this out. What is I cross J? I cross J. Well, it's actually set up so that if you go into your 3D coordinate system, with your I in the x direction, y direction, the z direction will be the cross product, the z vector. Well, to figure this out, we have to go I, J, K, 1, 0, 0, 0, 1, 0, and do the determinant of that.
Let's do it.
Well, you got I times the minor of I, J times the minor of J, throw in the negative there, K times the minor of K. And so let's take a look here. Oopsie, I has got a determinant of 0, 0, 1, 0. That's 0. And J is 1, 0, 0, 0. That's 0. And K is 1, 0, 0, 1. This is something called the identity matrix, and it works out to be 1, so you just get K. So you do just get K. I cross J. Now, if you want to, you can set up here, this is for EC. For EC, you can set up a little chart, IJK, IJK, and you can tell me what you get when you cross all these. And let's say it's this first vector. This is the first vector, and this is the second. We just did I cross J, right? I cross J ends up being K. So, hold it, what's J cross I? Should be negative K. You can check it and so forth, but that's the theory we just talked about. Okay, so you can fill that out for a pip if you want to fill out that diagram. I think they all work out to be unit vectors or opposites of them. What about I cross I? What's going to happen with that? Remember, what's the magnitude of something? What's the sine of the angle between? The angle between two vectors is 0. They're cross product is going to be 0 because sine of 0, your magnitude will be 0. So you end up with a 0 vector. So, yeah, don't just write down I squared. Actually do it out and convince yourself that that works out to be 0. Here's a few more, a few more properties. U cross V plus W, what do you suppose? U cross V plus U cross W. It distributes. Cross product distributes over vector addition. And U is parallel to V if and only if the cross product, if U cross V equals 0. And we talked about the magnitude of U cross V equals 0. Okay? Because whether it's 0 or if they're in opposite directions from each other, the sign of both those is 0. Okay? Okay, find a non-zero vector perpendicular to the plane containing these points. This is where you have to be careful. Because the first step is critical, then it gets pretty easy. And you actually do have a cross product in your calculator too. I think by the time you get it entered in and find it, you could have just done this. These determinants are pretty quick. Even though it's a 3 by 3, your top row is IJK. So you're really only doing the arithmetic of 2 by 2 determinants. So it goes very quick. But getting the right determinants first is key. Now you gotta be careful here. What are we gonna take the cross product of? 2 vectors, and these are points.
So do you have to go through them?
Oh,
Right.
you do like PQ and
So yeah, you gotta figure out PQ, the vector PQ, which is from P to Q. Can anybody eyeball that for me? 1, 5, negative 3. You're going over 1 in the x, up 5 in the, over the 5 in the y, and then back 3 in the z. 1, 5, negative 3. So everybody see where we came up with that vector? We went between 2 points. Because it's not enough to just take a cross product of 2 points in 3 space. This is going to be so wrong. Because imagine that back board there is the plane I'm trying to describe, and there's 3 points on it. If I take the cross product of 2 points, boom, boom, and treat those points as vectors coming out of the origin like this, my cross product is going to be heading up this way. And it's not perpendicular to the plane I'm looking for. But instead, okay, now my head is going perpendicular to the plane I'm looking for, right? So you've got to get your vector in the plane first, okay? You can't just use these 2 points. Okay? So we're not going to blow that, right? That's the most common mistake. Kids are anxious to get moved. Oh, it's cross product, it's cross product. I'm going to take cross product of these 2. Totally ignore it. Nothing to do with it. Has everything to do with it, right? What'd you do with the mic? All right, here we go. We need another vector, and it can be anything you like. QR, PR. I like PR only because I think the arithmetic is going to be easier. But you could have used QR, you could have used RP. How about QP?
No, that's not a vector.
Yeah, and when you get QP cross with PQ, those are vectors parallel to each other, and you're going to end up 0, and that's not going to be such a good thing for a normal. Okay. All right. So PR then from P to R is 2, 1, 1. Yeah, see that's nice, Chris. Now a non-zero vector. See, that's the other key thing. Non-zero vector. If you'd done QP times PQ, that would have crossed with PQ. That would appear something else. So I'm going to call this vector n with a bar over it. It's a nice symbol for the normal vector to the plane we're looking for in the next step. And it's going to be the cross product of these 2, PQ cross with PR. So that's IJK, and PQ is 1, 5, negative 3, and PR is 2, 1, 1. Okay, let's sneak another page in here. Sneak another page in. Okay, any volunteers to expand this one out?
So it's 8.
No, you got to go up there and make up for into class. What did we learn from this? Can you trust Michelle?
That's a -3, right?
Yes. Skipping the whole thing. No, go for it. We'll see if your answer's accurate. While we're waiting, you can get out your TI-89 and actually perform a cross product. The cross product is conveniently in one of those menus. If you can't remember, let's just go to our catalog. C for cross product. Oh, there's so many C things you could do. Walk me. Cross P it's called. Cross P, okay? Cross P, and now it gives you a hint there. It says vec1, vec2. So you got to put the vector in, and the vector has to be a bracketed thing with those square braces you see above the comma.
Curly brace.
So no, not a curly brace, not a brace. That would be for lists.
I like curly brace.
So then see how that works. You try with the curly brace and see if it does it for you. And I'm getting left bracket, and what's the first vector? 1, 5, -3. Okay, Britt, this had better be right. Now, you do have to put a comma in because I saw in the argument it said vector 1, comma. Because we're not entering a matrix now, we're entering two separated vectors here. And then brackets, and the other one is 2, comma 1, comma 1. Really?
Yeah.
Even with all our TI-89 says, here's the TI-89 command, cross P, left parentheses, bracket, 1, comma 5, comma -3, bracket, comma, bracket, 2, comma 1, comma 1, bracket in parentheses. Yeah, TI-89 says 8, -7, -9. You are exonerated, okay, Chris? All right. Do you mind, though, if I just show people this step again? I times the minor of I, which is 5, -3, 1, 1. Minus J times the minor of J, which was 1, -3, 2, 1. Plus K times the minor of K, which is 1, 5, 2, 1. Okay? And sure enough, yeah, your weight did work. 1, 5, 2, 1, 1 minus 10, yep. Yeah, very accurate. Well, what Britt did would have been sufficient. Okay? The key thing is that, see, you're doing the cross product. You should set up the cross product, so I know you're setting up the cross product, right? You put the right things into it. But after that, then, this, what Britt did is sufficient work, because she showed me. She separated out the IJKs. Now, the equation of the plane through those same 3 points again. Now, remember our work from 2 sections ago. What do you need for the equation of the plane?
Hey, isn't this the same thing? Slopes.
The vector n gives the coefficients. We don't need the slope. A, B, and C. In AX plus BY plus CZ equals D. So that's why we did the cross product. 8, it's going to be 8x minus 7y plus minus 9z equals D. Is that the equation?
But isn't the cross product?
I know, yeah, the cross product itself is not in the plane. It's a vector perpendicular to the plane. And that is our best way then to determine the direction of the plane. It's not by giving something perpendicular to it. Okay? You can't just say one slope. Like my plane has a slope of 3. Over 1 and up 3. That could be like this. It could be like this. Right? Yeah, which actually, what do we mean by rise over the run? Rise over the run over the wiggle? Is that we're going to try and come up with a 3-way division? That's not going to work so well. So this is our best bet then. giving the vector perpendicular to the plane. So now when you move that perpendicular vector, you can move the whole plane. Right? And that determines the direction of the plane. I know, it seems kind of backwards, because you're given your slope vector now, it's not really the slope vector at all. It's something perpendicular to the plane. But we're not done yet. How do you find D? That's right, Jack. Which one?
The Jack.
It's your choice. Choose wisely now. P, that's good. One's got a 0 in it, and the numbers are small. So let's plug in P, which is 103. So 8 times 1.
8.
That's correct. 8 times 1 minus 7 times 0 minus 9 times 3 equals D. So you get 8 minus 27. Oh, it's one of those tricky ones, negative 19. Is that the answer? D equals negative 19. No, that's a constant. You got to put it back into your equation. So your plane is 8x minus 7y minus 9z equals negative 19. And I think you'll find the other ones work, right? You put 2, 5, 0 in, you get 16 minus 35, that's negative 19. You put in 3, 1, 4, that's 24 minus 7 is minus 36, that's negative 19, right? So it works for all three. Yeah. Now, find the area of the parallelogram with sides PQ and PR. This is the other reason I want to pick PQ and PR. Correct. It's the magnitude of PQ crossed with PR. So it's the magnitude of, what was the vector we ended up with? 8, negative 7, negative 9. So that's square root of 8 squared plus negative 7 squared plus negative 9. Okay? 64 and 49 and 81. Can't you just call it 8 and 7 and 9?
13.9.
Don't go there, people.
It's about 13.9.
It's about 13.9.
Yeah.
I'm getting 120, getting 130, getting 194. Square root of 194. 196 would be 14. So yeah, 13.9 sounds good. About 13.9. Okay? Now, that's it for that note. So for the rest of the time, what are we going to do until like next Monday? Chris, it's a short week this week, right?
Baseball.
I'll let you know if we're going to delay the test. I'll let you know.
Class tomorrow.
And we don't have class tomorrow. Okay, so okay.
So let's relearn.
What can you do to determine a plane? What do you need to determine a
3
unique plane?
points to determine its plane.
3 points, that's what we just did, right?
Yeah, point in a line.
And so you'll be set on the final, the optional section at the end if you can do that. But there's some other cool ways to do it. Sam?
Line and a point.
Line and a point not on the line.
Not on the line.
That will determine a unique plane. Okay, Tyler? Two intersecting lines. Make sure they're only intersecting at any point. It's not the same plane intersecting itself. So 2 lines making an X. There you go. 2 unique parallel lines would determine the plane too.
So just 2 lines there.
What about skew lines?
Oh no. Oh no.
Now you're not going to get one flat piece of cardboard to cover those, right? You get really twisted.
What about a Oompa Loompa?
Oompa Loompa line like this?
I like Oompa Loompa.
Yeah, that would make it. Now, so let's see how you did. 3 non-collinear points, 2 unique parallel lines. There, we got that one. 2 intersecting lines, you got that one. A line and point not on that line. A set of points equidistant from the endpoints of the line segment. We forgot that one. That's kind of a strange way to state it.
Diwa.
That's because she's reading off the PowerPoint.
Okay, Zach and Lucas. Okay, we're getting some big stuff from them here. Yeah. Let's stop that.